Hello again. What we're going to move on to is section 3.7, which is concerned with optimization problems. What they mean by optimization problems is situations where you need to find the maximum or the minimum of something. And to do that, we need to write a function that describes something. So the new thing about these problems, you know how to find the maximum minimum value of a function now. That's not a problem. But in these problems, you have to come up with the function. So that's what makes them difficult. We're going to start with problem 14 from section 3.7, which is a classic. Every calculus student who's ever taken calculus in the whole world, back to Newton, had to solve this kind of problem. You have a box with a square base. Okay, so I'm going to try to draw a box. Okay, here's my box. I'm trying to draw it as square as I can. Okay, here's my box. I'm trying to draw a square box. It's supposed to be square box. What do they mean by that? That every dimension is the same, right? It's a cube. Well, actually, it's not a cube. We know it has a square base. Okay, so we know the dimensions of the base, let's say, are x by x. We don't know the height. They don't say it's a perfect cube. So we'll say that's h, that's its height. Okay, a box with a square base and an open top. So we have material on each side of the box, and of course on the bottom, but not on the top. The top is open, no material. And we must have a volume of 32,000 cubic centimeters. So we want our volume to be 32,000 cubic centimeters. That's what we need. Now what they say is, find the dimensions of the box that minimizes the amount of material used. So you have to minimize amount of material used. Okay, so how do we do that? Well, we need an expression for the amount of material used. We need to know how much material we use to make this box. Once we write that, then maybe we can figure something out. That's what we want to minimize. So let's call the amount of material used big A. And let's see how we can write it. Well, it would be the area of each face of the box, right? So on the bottom, we'd have x squared. That would be the area of the base. And on the sides, we have 1, 2, 3, 4 sides. And each of those areas is x times h. Okay. But we don't include the top, right? Because it's an open top. There's the amount of material we use. Uh-oh. We've got two variables, an x and an h. How do we do that? Well, we've got another bit of information that we can use. So we want to minimize this. We want to find the x that will give us the minimum value for that, or the h. Okay, so we've got this volume. What's the volume of a cube? It would be, or a prism, a rectangular prism. It would be the area of the base times the height. Multiply each of the dimensions. Okay, now what? Now we've got that 32,000 equals x squared times h. Okay? What we can do is solve for h. Divide both sides by x squared. And then we could put that into this formula for h, and then we would have a just in terms of x. So I'm going to do that. So I'm going to put this h in here. 32,000 divided by x squared. Good. Okay, I'm going to get rid of this now so we have more room to write. But you can keep it written down. Okay, so now we can simplify this, right? We can say this a is equal to x squared plus 4 times 32,000, which would be 128,000, right? 104 times, 128,000. Cancel an x with one of those. Okay. This is the hard part, getting that function. Now we take the derivative of this. So this is a as a function of x. So we can take the derivative of that. A prime of x equals 2x. Then remember, this is like x to the negative 1. So we'd have to bring the negative 1 down and decrease the exponent by 1. So it would be like that. So now we've got to figure out where that's 0. Because where that 0 would be the minimum or the maximum. So we have to get 2x minus 128,000 over x squared equals 0. Now, x can't be 0 or we wouldn't have a box. It can't be negative because we don't know what it means to have a dimension that's negative. So x has got to be greater than 0. So we can multiply everything by x squared and get 2x cubed minus, I'm multiplying this by x squared, this by x squared, this by x squared. So the x squared cancels here. So now I can solve that. If I solve that, I would get x cubed equal to, so it would be 64,000. So what does that mean? What does that mean? Let's see. What's the cube root of 64,000? Well, you could put that in your calculator and figure out what that is. Let's put it in the calculator. 64,000 to the 1/3 would be the cube root. 40. 40 what? Well, now, are we sure that that's a minimum? Is this a minimum? So we're saying that at x equals to 40, we think this function will have a local minimum. You can check that. You can check that by looking at the second derivative and saying, oh, well, the second derivative, if I take the derivative again, I'm going to have 2 minus, well, I'm going to bring the negative 2 down, so it'll be 2 plus 2 times 128,000 over x cubed. Well, at 40, at x equal to 40, that's positive, so the function's definitely concave up. So I know that if I make a box with a square base of 40 centimeters, so x has to be 40 centimeters, and the height has to be, well, remember the height was, when we substituted in the height, I'm trying to remember what the height was. I believe that was 64,000 over x squared. Is that right? Let me see, I can't remember. So the height, It's 32,000, sorry. So if the height is 32,000 over 40 squared, so the height would be 20 centimeters. And we can check that 40 squared times 20 had better be 32,000, and it is. So if we want a volume of 32,000 cubic centimeters, we need, and a square base for the box, then our square base is 40 by 40 and our height is 20. That'll minimize the amount of materials that we have to use. Okay, that's number 14, and I'll be back with another classic example of applying optimization.